Hi, and welcome again to the probability lectures here on Educator.com. My name is Will Murray, and we're working through a chapter on bivariate density and distribution functions. So everything in this chapter will have two variables, a y1 and a y2. And today we're going to talk about the expected value of a function of random variables. So that's something that we've seen in the single variable case, and we'll see how the same ideas extend to the multivariable case. I do want to start by reviewing the single variable case because I think it'll make the definitions make more sense for the multivariable case. So this is kind of a review of stuff you've seen before. The expected value of a variable, remember if it's a discrete variable, what you do is you sum up over all the possible values of the variable, and then you just have y by itself times the probability of that particular value of y. And then the analogous definition for the continuous case is that instead of summing, you take an integral, and instead of p of y, you have f of y, which is the density function, but you still have this y multiplied on it. And then we can also talk about the expected value, instead of y itself, the expected value of g of y, which is some function. So for example, you might have g of y to be y squared, and the way you define that, if it's discrete, is you sum up over all the values of y, and you still have the probability of each value of y there. But the difference is that instead of the y that we had before, we replace that with g of y. And then the same kind of thing in the continuous case, we take an integral, we still have the density function f of y, and then we replace the y that we had before with a g of y, and then we have to solve that integral to find the expected value. So the multivariable case is the new stuff that we're going to learn in this lecture, and the definitions are very similar, except that instead of single sums, we'll have double sums, except instead of single integrals, we'll have double integrals. So let's take a look at that. In the bivariate case, we'll have a function of two variables. So g is now a function of y1 and y2. And instead of a single sum, we have a double sum because there's two variables here. There's a y1 and there's a y2. We still have the probability function, except it has two variables now, p of y1, y2. And then the expected value of g of y1, y2, you just multiply it on. Instead of g of y, we have g of y1, y2. So it's very similar to the single variable case, except that we have a y1 and a y2. In the bivariate case, we still have that joint density function f of y1, y2. And again, we're integrating over both y2 and y1. And instead of g of y, we have g of y1, y2. So we'll be doing a lot of double integrals in this lecture. I hope you're really fresh on your Calculus 3, your multivariable calculus, because you will need to be able to do a lot of double integrals to solve the examples in this lecture. Before we jump into the examples, there's a few more facts I want to introduce you to. In particular, linearity of expectation is a very, very useful principle to invoke when you're calculating expected values. So the expected value of a constant is just a constant by itself, and expectation is linear in the sense that if you have a constant multiplied by a function, what you can do is just factor that constant on out of the expected value there. So it just factored out to the outside there. And that sometimes makes things a lot easier just because you can pull all the constants outside and not worry about them when you're doing your integral. Even more useful is additivity. If you have a sum of two functions and you want to find their expected value, what you can do is calculate their expected value separately and then just add them together. So that's extremely useful if you're trying to find the expected value of something plus something else. Just find their expected values separately and then add them together. We'll see some examples when we get to the problems of how that can be really useful. It can save you doing a lot of very complicated integrals and sometimes reduce them to much simpler integrals. So let's go ahead and start in on the examples. First example here, we have a joint density function of e to the negative y2. Remember that colon equals just means is defined to be. So our joint density function is defined to be e to the negative y2, and y1 and y2 are both between 0 and infinity, but y2 is always bigger than y1. and we want to calculate the expected value of y1 plus y2. So right away what I'm going to do is draw a graph of this region, because it's not a perfectly square region. It's not totally obvious what the region is. So I think the easiest thing is to start out with a graph. There's y1 on my horizontal axis, there's y2 on my vertical axis, and now I'm going to graph the region, the line y1 equals y2. If you were x and y, it'd just be the line y equals x. So that's that diagonal line right there. That's the line y1 equals y2. And what we want to look at is the region where y2 is bigger than y1. So that's the region above that line. Let me go ahead and color that in. So there's that region right there. And I want to describe that region because I'm going to be setting up a double integral to calculate this expected value. And it looks to me like it's easiest to describe it. Let me draw this in red. It's easiest to describe it listing my y2 first and then my y1 in terms of y2. The point of that is that I'll have one more zero to deal with when I set up my limit, so that'll make things a little bit easier. So if I list y2 first, my y2 will go from 0 to infinity, and my y1 goes from y1 equals 0, that's the vertical axis, up to that diagonal line. So that's the line y1 is equal to y2. So that's a good way to describe the region. We'll use that to set up a double integral to find this expected value. So this expected value of y1 plus y2 is equal to the double integral, I'll fill in the limits in a second, of y1 plus y2 times the joint density function, the f of y1, y2, which is e to the negative y2. And now let me fill in the limits on the integral. Y2 goes from, oops, that was y2, goes from 0 to infinity. Y2 equals 0 to y2. We'll take the limit as it goes to infinity. And y1 goes from 0 to y2. Whoops, not 2, but y2. And that means I'm going to integrate y1 first because it's on the inside, so I'll put dy1 on the inside and dy2 on the outside. So let me go ahead and do that integral. Of course, if you're fortunate enough that you can use software for all your integrals, at this point you can just drop the whole thing right into a computer algebra system, something like MATLAB or Mathematica or something like that, and it would just spit out an answer for you. So if you're fortunate to have access to that, then go ahead and do that. I want to go ahead and work out the integral just to show you that it's not that bad. It can be done by hand. So I'm going to do that first integral. Notice that the inside integral, the variable is y1. So that means y2 is a constant, and in particular, the e to the negative y2 is a constant. So I'm going to separate out that e to the negative y2, and then the integral of y1 plus y2 with respect to y1 is y1 squared over 2 plus y2 y1. So I just did that inside integral with respect to y1. Now I have to evaluate that from y1 equals 0 to y1 equals y2. And so I'll get e to the negative y2. And I see I'm going to get, if I plug in y1 equals y2, I'll get y2 squared over 2 plus y2 squared. And I see I can combine those into 3 halves. E to the negative y2 and y2 squared. 3 halves y2 squared, e to the negative y2. And that was just doing the inside integral, so I still need to evaluate the outside integral. y2 equals 0 to y2 goes to infinity of this expression here. This is dy2. And I'm integrating x squared e to the negative x. That's a classic case for integration by parts. Let me go ahead and set up a little table to do my integration by parts. y2 squared, I'm going to pull the 3 halves out because that's really not relevant. Not going to be, it's not going to change anything in the integration by parts. and e to the negative y2. Now this is kind of my little shorthand trick for doing integration by parts. If you don't know this trick, or if you are rusty on integration by parts, we've got some lectures. It's in the Level 2 College Calculus section here on Educator.com. So there's a whole lecture on integration by parts. You can just check it out and get all caught up to speed. But for the time being, I'm just going to use my shorthand trick, which is to take derivatives on the left, so that's 2y2, and then 2, and then 0, and integrals on the right, so negative e to the negative y2, and then positive e to the negative y2, and then negative e to the negative y2. And then you'd make these little diagonal hashes with a plus, minus, plus, and then you sort of multiply down the diagonals and read off the answer. So this is 3/2 times y2, well, it's negative because there's a negative there, negative y2 squared e to the negative y2, minus 2y2 e to the negative y2, minus 2 e to the negative y2. And then all of this needs to be evaluated from y2 starting at 0, and then we'll take the limit as it goes to infinity. So let's sort that out. We still got this 3/2. When we plug in y2 going to infinity, all of these terms are going to disappear. There's a little bit of L'Hopital's rule in there that I'm not really showing you the details of, but basically the e to the negative y2 term dominates, and it takes everything to 0, and even though it's being multiplied by infinity. So if you wanted to check the details of that, just go through L'Hopital's rule and check that out. But all the terms at infinity are going to go to 0. So 0 minus 0 minus 0. Now I'm going to plug in y2 equals 0, and I'll get minus a minus, so plus, but it's 0 anyway. Minus a minus, so plus, but it's 0 anyway. Minus a minus, so it's plus 2 e to the 0, which is just 1, so plus 2. And all those zeros disappear. I've got 3/2 times 2. And so my answer, my expected value of y1 plus y2, is 3. And that finishes that problem. Let me go back over the steps and make sure that everybody's clear on everything. Kind of the first thing to do here is to graph the region. So I looked at those limits there. y1 and y2 both go to infinity, but y1 is always less than y2. So that's how I got this region right here, this triangular region that goes on infinitely far. And then I wanted to describe that region in terms of y1 and y2. And I thought it'd be easier to list y2 first, because then I could get a 0 for the lower bound on y1. That makes my life slightly easier to have that 0 there. So that's why I picked y2 to list first. It could also have done it with y1 first, but it would have made it a little more messy. So then I used those limits to set up this integral right here. And because it's y1 plus y2, that's why I multiplied everything by y1 plus y2. And then I used the density function to get this e to the negative y2. And now it's just a calculus 3 problem. The only thing you have to be careful about is which variable you're integrating with respect to. So at first I'm integrating with respect to y1, which means y2 is a constant. That's why I got these different answers for y1 and y2, because the variable of integration was y1. Plugged in my values for y1, and now it simplifies down to a value, an integral in terms of y2, which is something that I needed parts for. So that's where I kind of outsourced to this tabular integration technique to do integration by parts. And that came back and gave me the answer, this long answer. Then I plugged in my bounds, 0 and infinity, and the infinity terms all dropped out. That's really showing some L'Hopital's rule there. Well, I didn't show the L'Hopital's rule, but that's kind of what was going on in the background there. So the infinity terms all dropped out, and most of the 0 terms dropped out, but this 0 term gave me a value of 2. And when I multiplied that by 3/2, that's how I got my expected value of 3. In example 2 here, we've got a joint density function of 2 times 1 minus y2, and y1 and y2 are both bigger than 0 and less than 1. Let me graph that before we go any farther. That's a simpler region than we had in example 1 because that's just a square region. Here's y1 and here's y2, and there's 0 and there's 1 and there's 1. So we're just looking at a square region here. And so let me color that in. And we will need to integrate that, so we'll need to describe that region. So it's very easy to describe as y1 goes from 0 to 1, and y2 goes from 0 to 1. And now let's go ahead and figure out what we're calculating. E of y1, y2, the expected value of y1 times y2. So remember, the way you calculate that is you set up a double integral on your region. Y1 equals 0 to 1. And actually, maybe I'll list the y2 on the outside. They're both constants, so it'll work the same way either way. So y2 equals 0 to y2 equals 1. y1 equals 0 to y1 equals 1. And now, the function that I'm trying to find the expected value of is y1, y2. So I'll multiply y1, y2 in there, and then I'll put in the density function that we're given, which is 2 times 1 minus y2. And now the way I've got it set up, my first integral is dy1, and my outside integral is dy2. So I'm going to go ahead and solve that integral, the first one on the inside. I'm integrating with respect to y1. So I see I have a 2y1. I'm going to use those together and just get y1 squared. And then everything else is a constant because I'm integrating with respect to y1. So y2 times 1 minus y2. And I evaluate that from y1 equals 0 to y1 equals 1. If I plug in y1 equals 1, I just get y2 times 1 minus y2. And y1 equals 0 just drops out. So this is what I'm integrating. And I'm integrating this dy2. And so that's y2 minus y2 squared. Well, the integral of y2 is y2 squared over 2. The integral of y2 squared is y2 cubed over 3. And I need to evaluate that from y2 equals 0 to y2 equals 1. And so if I plug in y2 equals 1, I get 1/2 minus 1/3. Plug in y2 equals 0, they're both 0. And so 1/2 minus 1/3, if you put that over a common denominator, is 3/6 minus 2/6. So my expected value of y1 times y2 is exactly 1/6. So that finishes that problem, but let me recap the steps. First thing I did was I looked at the region there, and I drew a graph there. y1 and y2 are both between 0 and 1, so I got a square. And then I described that region in terms of y1 and y2. They're both constants because it's a square region. And then I used that to set up a double integral. And the y1, y2 here, that came from the fact that we were trying to find the expected value of y1, y2. And then the 2 times 1 minus y2 came from the density function that we were given. So at that point, it's just a calculus 3 problem, multivariable calculus, solving a double integral. The important thing to notice is that the first variable of integration, the inside one, is dy1. So that's why all the y2's were just constants, and I integrated 2y1 to get y1 squared. Dropped in my values for y1, and it simplified down to something in terms of y2. So I integrated that with respect to y2, dropped in my values for y2, and got a number that represents the expected value of y1 times y2. In example 3, we have two variables, y1 and y2. We haven't been told the joint density function, but what we have been told is that the mean of y1 is 7 and the mean of y2 is 5. And now we have a couple of functions defined here u1 is y1 plus 2y2, and u2 is y1 minus y2, and we have to calculate the expected values of the u's. So the point of this problem is to milk linearity of expectation. So if you don't remember that, go back to the introductory slides for this lecture and look for the one called linearity of expectation. That's what we're going to use very heavily to solve this problem. Linearity of expectation is the key to solving this problem. And so the expected value of u1 is equal to the expected value, just by definition of u1, of y1 plus 2y2. But then expectation is linear, so we can separate this out into the expected value of y1 plus 2 times the expected value of y2. And so now we can just plug in the means that we've been given. So the mean of y1 was 7, and the mean of y2 is 5. 7 plus, let's see, 7 plus 2 times 5 is 7 plus 10, so that's 17. I almost got tripped up on my arithmetic at the end there. u2 behaves exactly the same way. The expected value of u2 is the expected value of y1 minus y2. And so that's, again, it splits up using linearity there. So that's the expected value of y1 minus the expected value of y2, which is 7 minus 5. And so our expected value of y1 minus y2 is 2. So we have an answer for both of those. The key to finding those answers was really the fact about linearity of expectation, that if you have the expected value, you can split it up and take expected values separately, and you can also pull out constants. That's true for expectation. By the way, that's not true for variance, so you don't want to be monkeying around with linearity of variance because there is no such thing. But for expectation, it is true. So what we did here was I just plugged in what u1 was, y1 plus 2y2, used linearity to split it up into expected values of y1 and y2, and then just dropped in those expected values. Remember, expected value and mean are the same thing. So I just dropped in the values of 7 and 5, and I got 17 there. And then the same thing for u2. I plugged in y1 minus y2, split it up, and dropped in my expected values of 7 and 5, and that's where that 2 came from. In example 4, we've got joint density function f of y1, y2 defined to be 6 times 1 minus y2, where y1 and y2 are both between 0 and 1, but y2 is bigger than y1. Let me graph out this region before we go any farther with that. So there's y2, here's y1, and we're looking between 0 and 1 on both axes, but we only want to take the region where y1 is bigger than y2. So that's sort of the area above the line y equals x. Let me draw that region, color that in a bit. So that blue region is what we're going to be looking at, and we're going to end up doing a double integral for this one, actually 2 double integrals. So I think it's going to be useful to describe the limits of this region. And I think I'd like, I switched my y1 and y2 on the axes. I'm not sure why I seem to like to do that, but I know I've done that several times. So y1 is always the horizontal axis, and y2 is always the vertical axis, or at least it should be if I wrote it down correctly. I think the best way to describe this is in terms of y2 first. So y2 has to be constants, goes from 0 to 1. And then y1 we can't use constants because then we get the whole square. We just want the region from y1 equals 0, 0 up to y1. That's that line there is the line y1 equals y2. So y1 stays less than or equal to y2. So that describes that triangular region. We're going to use that to set up a double integral, or actually a couple of double integrals, since we have 2 expected values to solve here. So The expected value of y1 is the double integral, and I'll follow those limits there. y2 goes from 0 to 1, and y1 goes from 0 up to y2. And now, since we're finding the expected value of y1, I'm going to multiply in a y1 times the density function, 6 times 1 minus y2. And then the inside integral is dy1, the outside integral is dy2. Now it's just a double integral problem, so we can solve it using what we learned in Calculus 3. So the first variable, the inside one, is dy1, which means that 1 minus y2 is just a big old constant. Now the integral of 6 times y1 is 3y1 squared. So 3y1 squared. And we want to integrate that, or evaluate that, from y1 equals 0 to y1 equals y2. So if I plug in my limits for y1, 3y1 squared will give me 3y2 squared. 3y2 squared times 1 minus y2, and then y1 equals 0 just drops out, so that one doesn't play a role. And so that's finishing the first integral. Still need to integrate that with respect to y2. And so let's see, that's 3y, whoops, I changed my y1 to a y2. That's very important. So 3y2 squared times 1 is just 3y2 squared. That integrates to y2 cubed minus 3y2 cubed, so I have to integrate that. That would integrate to 3 times y2 to the 4th over 4. So 3/4 y2 to the 4th. And now I have to integrate that, to evaluate that from y2 equals 0 to y2 equals 1. And so if I plug in 1 to both of those, I get 1 minus 3/4. Plug in 0, y2 equals 0 to both of those, they both drop out, so minus 0. And so that simplifies down to 1 minus 3/4 is 1/4. That's my expected value for y1. And I still have to calculate the expected value of y2 because the problem asks for both of those. But I've already done some of the work. I've already described the region. So it'll be the same integral, y2 equals 0 to y2 equals 1. And y1 equals 0 to y1 equals y2. The same integral, except that instead of multiplying by y1, I'm going to multiply by y2 because that's what I'm finding the expected value of. So y2 times 6 times 1 minus y2. Now dy1 and dy2. So still going to do the inside integral, but since I'm integrating with respect to y1, all the variables here are in terms of y2, so I'm integrating just a huge constant. So it's 6y2 times 1 minus y2. That's all a constant, just times y1. And then I need to evaluate that from y1 equals 0 to y1 equals y2. And so let's see, if I plug in y1 equals y2, I'll get 6y2 squared times 1 minus y2, because there were there's a y2 there, and then that y1 becomes a y2 when I evaluate it. And if I plug in y1 equals 0, it just drops out. And so I have the integral. I have the integral from y2 equals 0 to 1 of 6y2 squared dy2. What I notice here is that that's the same as the integral I had above, 3y2 squared, 1 minus y2, except that I have a 6 instead of a 3. So that's 2 times the same integral as above. Maybe I can flag that here with a star. So this is 2 times integral star. And so if I evaluate that integral, what I'll just get is 2 times the answer that I got above. So 2 times 1/4, and 2 times 1/4 is just 1/2. So that gives me an answer for the expected value of y2 of being 1/2. Now, if you don't like the way I did that by sort of citing the integral above, just go ahead and work out this integral. It's just a calculus 1 problem. Shouldn't take you very long, and you should end up getting 1/2. It should work out. So that gives us both the answers that we were looking for. Let me remind you how we set that up. First thing I did, like all of these problems, is I looked at the region that was given to me, and I graphed the region. So in this case, y1 and y2 are both between 0 and 1, but y2 is bigger than y1. So I just looked at the region above that diagonal line, the y equals x line, and I decided that it was easier to describe that region if we kind of march horizontally. So that means describing the y2 first in terms of constants, and then describing y1 going from 0 to y2. If you just said y1 goes from 0 to 1, all of a sudden you've described a square, and that's not the region that we're looking at. So I set up those limits by looking at the region, and then I pulled those limits over and used them to set up a double integral. And now I took the density function, 6 times 1 minus y2, and I multiplied it by the thing we're finding the expected value of, which in the first case is y1, but in the second case is y2. And that's because of the different requirements. The first one is y1, and the second one is y2. And so in each case, I got a double integral to solve, and then I just did the double integral. I integrated dy1 first, which is why y1 turned into 6y1 turned into 3y1 squared, and 1 minus y2 was just a big old constant. Plugged in my values for y1, got an integral in terms of y2. Pretty easy integral in the sense of probably you could hand that off to a first semester calculus student and they could solve it for you, and the answer they would hopefully come up with would be 1/4. For y2, same kind of thing happens, except that when you're doing that first integral, there are no y1s at all, which means you're integrating a constant. So you just get that constant times y1, plug in the value of y1 equals y2, and we get 6y2 squared, 1 minus y2. And because I'm lazy, I noticed that that was the same integral that we had back here, except it's multiplied by 2, which means we can just take the old answer and multiply by 2. So 2 times 1/4 is 1/2. If you hadn't noticed that integral was the same as the previous one, that's okay. You just go ahead and work it out and do 1 or 2 more steps of calculus 1, and you'll get an answer. Now, I want you to really understand these two answers, and I want you to remember them, because the next example, example 5, we're going to be using these answers from example 4. So it's the same setup as in example 4, and then we're going to use these answers to take it a step or 2 farther. So make sure you understand these before you go on to example 5. All right, in example 5, we've got actually the same setup that we had from example 4, and we're going to be using the answers that we derived in example 4 to solve example 5. So if you haven't just watched example 4, go back and watch example 4, or work it on your own and just make sure your answers agree with mine. But you want to have those answers fresh in your mind and ready to go for example 5. So let me solve example 5. We're given this same setup. F of y1, y2 is 6 times 1 minus y2, and then they've described a region for us. So let me just emphasize that that is all the same as example 4, and because of that, I'm not even going to try to graph it like I did with all the other examples. So if you want to kind of work that out and you want my help, just go back and watch watch example 4, and you'll see that that is carefully worked out, and I drew the graph and everything. In this case, we don't have to do that again, because we're finding the expected value of 2y1 plus 3y2. So the expected value of 2y1 plus 3y2, the trick here is not to do an integral, but to use linearity of expectation. So that was something that I introduced you to on the 3rd introductory slide to this lecture, linearity of expectation, and it's super useful for problems like this. Expectation expectation. I should spell expectation right since it's such a useful concept. Linearity of expectation says you can distribute and split up these this expected value into 2 times the expected value of y1 plus 3 times the expected value of y2. And both of those were things that we calculated in example 4. So I'm not going to recalculate those now because we did no little job of work in calculating those. So the expected value for y1, back when we worked it out in example 4, was 1/4, and the expected value for y2 was 1/2. So go back and watch example 4 if you aren't sure where those numbers are coming from. So this is 2 times 1/4 is 1/2 plus 3/2, and that's just 4/2 or 2. So we got an answer right away. We didn't have to do another double integral. And the reason we didn't have to do another integral is because this is the same setup as example 4, and we already worked out kind of the basic values in example 4, and now we can just extend that using linearity of expectation. So if the phrase linearity of expectation doesn't quite trip off your tongue yet, it's worth going back and watching that third slide again, and you'll see how nicely it helps us in this problem, because it allows us to take 2y1 plus 3y2 and split it up and just find the expected values of y1 and y2 and then combine them back together. So those expected values we calculated in example 4 to be 1/4 and 1/2. So we just drop those numbers in and then simplify the fractions, and we get our expected value of 2 for 2y1 plus 3y2. So that wraps up this lecture on expected value of a function of random variables. Next up, we've got a lecture on covariance. It's a big topic, so there's a lot of good stuff in there. I hope you'll stick around for that. In the meantime, this is the chapter on bivariate density functions and distributions, and this is all part of the larger lecture series on probability here on Educator.com. My name is Will Murray. Thanks for joining me today. Bye-bye.